Today I will be tackling a TED Ed riddle called the Big Bang Riddle, and the way I like to do these is not to solve it with my clever brain, but to use code. I like to solve problems with code, so that's what I do, and I won't know the solution when I actually write the code, so that is something to keep in mind. All right, let's check it out.
It's moments after the Big Bang, and wow, you're still reeling. You're a particle of matter amidst a chaotic stew of forces, fusion, and annihilation. If you're lucky and avoid being destroyed by antimatter, you'll be the seed of a future galaxy. You gravitate towards a ring of particles that have devised a game. A friendly gluon explains there are an equal number of matter and antimatter particles. At the blow of a cosmic whistle, every particle of matter with a particle of antimatter to its immediate right will merge with that antiparticle.
I'm already thinking, because of the circular nature of things, I'm going to have to like create some kind of either a list or potential graph structure to kind of keep track of everything.
To poof, both annihilate. The circle will tighten to make a smaller circle, and the process will repeat until just one particle of matter remains. They've been waiting for someone like you, as with a perfectly balanced setup, no one would be left in the end. As guest of honor, they'll let you choose where to insert yourself into the ring. What spot should you choose to make sure you're the last particle standing?
Okay, so here are the rules. So now it says pause now. Okay, that's a little tricky. Okay, so we have three examples, and in each one we have to figure out where we want to stand. Okay, I think I can like start writing something up. All right, so here I am in a Jupyter notebook to write some Python code, and my proposed algorithm is, I don't think I want to use a list, even though I certainly could. You can certainly use a list, but I think it's more intuitive for me to use like object-oriented programming, just because that's what I'm very familiar with, and it's just a lot more intuitive to have like objects that I can kind of toy with. So given this concept, I'm going to go back a little bit, that the left, so whenever you're a matter particle, anytime that you have an antimatter to the right, you want to, that'll be, they'll cancel each other out. It's always better to be to the left of any group of matter particles. So essentially with that, we need to position ourselves to the left of the last surviving matter particle, or if there are more than one, any one of those will count, right? It's sort of like this iterative thing of rounds of annihilation, essentially. So I'm going to try and actually simulate that given those examples. All right, so I have tackled this with a object-oriented programming approach. It's very similar and reminiscent of a linked list. I actually made a video recently about that, so I'll link it here somewhere. But basically, I'm going to be implementing a particle class, which is essentially like a node in the graph structure, and then there's going to be a wrapper for that, which is like the circle, which houses the responsibility of like dealing with each round of annihilation. Here is the particle class. This is going to be an object. It will have three states. It'll be either a matter particle, antimatter particle, or the particle will be considered annihilated. It will have a reference to the left and right particles, so those are going to be object references. And then I have a flag here, and I'll show later why I have this, but basically I need a flag on the object so that I can tag it for annihilation. Because we're going through successive rounds, because we're in a circular graph structure, we want to flag it for annihilation instead of actually transitioning the state to annihilation, because then you won't really know, oh, have we already been to this node before, or this particle before? And then the state is just the current state. Is it matter? Is it antimatter? Is it annihilated? And the position, which allows me to distinguish where we are, but that's just to kind of distinguish and give each particle its own identity, essentially. Here I have a very simple method, which is to transition the particle properly to the annihilated state. And then we have a wrapper class called the circle, which will be able to handle and wrap around all the particles. This is responsible for handling those rounds of annihilation that I mentioned. All right, so each circle will start off with a list of particles. Again, those are going to be plus or minus. I just have to like type that in, essentially. And then I will initialize them and set the root. The root is essentially just the first particle in that circular graph. So it's somewhat arbitrary where you start. Here I have a matter count. I know that half of them are matter particles, so I just take the length of it and just divide by 2. Since this is floor division, that's going to give me an actual like integer that I can rely on to know how many matter particles are there currently in the circle. Okay, so here I'm calling init particle. So what does that do? That's what this is. We're going to start root with none, and the previous particle we want to consider, since we need to have a reference to whatever the previous particle is. Keeping a reference to the root is just allowing us to return it later when we set the root here. All right, so we just go through the list. I'm enumerating so that I have an index, and that'll be essentially the ID for the particle. And then I create the particle and make sure the type is the same. So this particles list is going to just be plus or minus essentially, which represents whether it's a matter or antimatter particle. And I set the position as I. And that's all the particle needs to get started. If there is no root, I set it. Otherwise, I take the previous particles dot right reference and set it to the current particle, and then I do vice versa basically. So I need to take this current particle's left reference and point to the previous particle. This just allows us to have a double link to have reference to both the left and right. Well, hold on a second. I'm now realizing now that I finished coding the solution, I figured out what to do. I actually never end up using the left reference, to be honest, because you never need to go back. So this is like not needed. Not needed, never used it in solution. And to be sure, and I already know this going in, like I'm over engineering this. I know that just because when I was doing it, I was like not really sure how to work with the problem. In hindsight, I could probably have solved this with just a straight up list, probably, but whatever. It worked out. I'm not going to stress out too much about it. Once I have my previous particle set, I can just keep looping, and as long as I keep a reference to the previous particle, then I'm able to link everything up. So once you're done with this for loop, you will now have two tail ends that are essentially disconnected, and the last step is just to link the last one with the first one, which is the root. And now that those are connected, you're able to say you're done and return the root. And that will be our like root particle to just start things off with. Did have some visualization that I want to do just so I can actually see what's going on. So I had a simple function here called print circle. I just take the particle states, will basically be like grabbing as we're going down the circle. So I have here a set called considered. This is just going to ensure that we don't go over something that we've already seen, because we do have a circular graph that we're dealing with. So we have to be mindful of that. So I set the current particle for consideration as the root, and then while the position, which is again a unique identifier for each particle, is not in the considered set, then I know that I haven't kind of looped back on myself. So I can add that to the considered set, and then I will start thinking, okay, well, if I'm in a annihilated state, that particular particle is annihilated, then I definitely don't want to consider it, right? But if it's not annihilated, then that's the one I do want to consider. And so I add that to my particle states list that's growing. And I'm just going to have the state and with a reference also to its index. And we'll see what that printout looks like. It's just going to be like plus or minus with a backslash, which is here, and then the actual position, which is a unique identifier for each particle. And then I just keep going right. And I do a printout here. I have like 3 little dots. And then I join with the particle states, which will be all these strings together. And then I have 3 little dots here just to kind of represent that it's a circular graph. And so I don't want to forget that essentially. Okay, so the next method is called annihilate. And this is the main workhorse of the wrapper circle class. And what we start off with is a list of to be annihilated. This is essentially just us collecting the particles that are going to be annihilated, and then we do the annihilation after we've gone through the circle one time, basically. We want to make sure to not change the state right away, because then we won't really know, oh, have we already been over this? So we don't want to go over ground we've already covered. All right, so here I set my current particle for consideration. I basically check, okay, while this has not been set to be annihilated flag, this is nice because essentially I'm going to keep looping until I hit a particle that is flagged for annihilation. That is a signal to say, hey, we've already been here, we can stop. Okay, so as a quick note here, we're only going to be moving right. And the reason for that is because of the logic that we're told that only antimatter particles that are to the right of a matter particle are actually going to cause an annihilation event. And so that's why we are always moving right. Another thing to consider is we don't need to consider any other particles except for matter particles. So if the current particle is not a matter particle, hey, guess what? You don't matter. Okay, all right. And so you just set the current particle to the right and you just hit continue so that the loop continues. Once you're past this, then you know for sure that the current particle is a matter particle. So because this is a matter particle, it is potentially the left half of the pair that will be annihilated. So I'll just secure it as a variable called left matter particle, and then I'll just continue on the current particle as like what is to the right of that. We can skip over any particles that have already been annihilated because they're not really there, right? So I have here just a little while loop here that basically says while the current particle is annihilated, we'll just kind of keep skipping ahead until we get to something that's not in the annihilated state. And then the logic for annihilation is the one case and the only case where the current particle is an antimatter particle. This is essentially the right half of the pair. If it is an antimatter particle, then we know that's an annihilation event. So we're going to set them to have the flag to be annihilated as true, and we're going to just add those particles, the actual objects, to the growing list of to be annihilated. You know what? I think I don't like that naming because I have a flag here called to be annihilated, and then I also have a list here called to be annihilated. So I want to make it very clear. So I'm going to say this is the to be annihilated list. Okay, and then I just basically set my current particle to the next one on the right because we're essentially like eliminating it. So the thing that we want to consider next in the while loop will be whatever that next particle is. Once we're done with this while loop, we know for certain that we have gone through the circle one time and we've considered every possible combination, and we know we can now start annihilating. And then we go through the annihilation step, which is simply to go through our to be annihilated list. And for each particle, we check, oh, are you a matter particle? If you are, then we're going to decrement our matter count by 1. That's something we'll keep track of for later. Then we can just say, hey, particle, go ahead and be annihilated. Okay, so once we're done with that single annihilation method, we'll now want to call that over and over again to figure out where is the last matter particle before everything gets annihilated. Because as long as we have that, we can position ourselves just to the left of that last matter particle, and then we're in the safe zone, and we can say that's our answer. Okay, so this is what that method does: get last survivor position. It will we'll start off with a set here called survivor position. This is essentially going to allow us to keep track of the matter particles that survived from the last round. Every time that we do an annihilation round, we are actually changing the state of those particles. So we won't be able to know, oh, what's surviving after you've done the annihilation. So you need to kind of keep track of it from the last time. So that's what we're going to be using there. I have an iterator here. This is just to keep track of how many rounds we've had. For having this verbose flag as true, it just prints out some nice things. I also have the print circle method from before, so that's helpful just to kind of see and visualize what's going on. Other than that, we have a while loop here that is going to keep going, and by that I mean we're going to keep running annihilate when we have matter particles. So this matter count was set, and I should say changed, whenever we do a proper annihilation of a matter particle. So this is the current number of matter particles that are still around that have not been annihilated. Once we're done with one annihilation round, let's say we go through this the first time, we need to now consider, okay, well, how many matter particles are left? Because those are the ones that are surviving. So we need to record those survivor positions, and by that I mean like the identifier, the index, and that's what this code over here is doing. First, I'll set my current particle to the root, as we typically do. I have here a variable called past first, set to false. Effectively, this is all because we're in a circular graph, and so we need to keep track of it and make sure that we're not overwriting what we've already looked at. And so this allows us to make sure we don't do that. You'll notice my while loop here has this little bit of logic here. The very first particle we consider is the root. It is position 0, which would be a really nice indicator of, hey, you've seen this before. But the very first time you go through it, that's going to be true, right? So we don't want to have that fail right away. So I have this variable called past first, which is initially set to false. And so once you get through this loop one time, it will automatically be set to true. So that I should say the second time we see the particle position as 0, then we'll know, oh, this is true and this is true. Therefore, this negation will be false, and we can exit our while loop. So this is just a way of ensuring that we go through each particle once. That is all that's doing. As we consider a particle, we'll say, hey, are you a matter particle? If you are, we can add your unique identifier, your index or position, to this temporary set called temp survivor position. Once you get through all this, you've essentially counted up and tallied and kept track of all of the indices of surviving matter particles in this set. If that set has any kind of length, that means you have survivors, and we can overwrite our outer survivor position set. We'll basically keep doing that while we have matter. Once we don't have any matter particles after a round of annihilation, this will be empty, and therefore there will be no length. We'll exit out of this loop without having overwritten the survivor position set, and that means we're going to have like the previous survivor positions, and that is what we will be returning. So at the end, we will return a set of indices for matter particles that survive until the very last annihilation. And then all we have to do is position ourselves to the left of that position. And that is basically it. So I'm going to run this, and I'm going to consider our first circle here, this like little small circle on the left here. I basically coded it up here as a list of, plus or minus one. I'm using the particle reference here because that's, I think, better coding. So I started, this particular matter particle is referring to this one here. Not that it really matters because it's all a circle anyway. All right, so we have that. I'm going to create a circle here, and we can see our last survivor position as verbose equals true, and you get to kind of see the printout here of the very first position. This is before anything happens, so this is round 0. So round 0, we have a matter particle. That's what this is. In fact, we have 3 of them right next to each other, 1, 2, 3. So you can kind of see like how the printout works. And then after one round of annihilation, we can already kind of see what's going to happen because we have a matter particle right next to an antimatter particle. And I should say the antimatter particle is to the right of that one. So 2 and 3 are going to be annihilated, and then also 5 and 6 should be annihilated. And that's exactly what we see here. After the first round, those are missing, they're gone because they've been annihilated, and then you can just keep going basically. And the last one, the last survivor, is this one, index 0, and we get to return that as our result. So we know if we wanted to, we would position ourselves to the left of the 0 index particle, which is essentially this one here. So this question is a little different because it doesn't ask you just for an answer, it asks you to come up with a strategy. So this solution of mine isn't going to allow me to do that, since I'm just writing code and just like figuring out the solution in an automatic programmatic way. And that doesn't really lend itself well to me having an actual strategy. I need to figure that out using my actual brain a little bit. So unfortunately, I did have to use my brain a little for this, but I think it's okay. So in order for me to use my brain a little bit to make a strategy, I have some interpretation here of these findings. I'm not really diving too deeply into this. I'm just kind of seeing what the code is producing and trying to figure it out. So when I saw this 0 and I look back at the picture, I'm thinking, oh, it kind of makes sense because you have a kind of long continuous string of matter particles next to each other. So you just want to be to the left of that. So that's my interpretation for this first one. Being at the leftmost on the largest group of consecutive matter particles is best. Let's check out the second circle. So that's this circle here in the middle. I've coded it up here. It's just, I think it's 3 antimatters. So I think I'm starting like right here on this spot. And let's run that. And let's run this to get the last surviving position. Okay, so this one has index 5. That means it's this one here. And it kind of makes sense because you see how it's like, it's like this kind of long-ish continuous set of matter particles, like it's just to the left of that. So if I look up to the picture, it's this one right here. So I think it kind of makes sense. We see a number of matter particles, but this is the longest continual string of them, and so it makes sense to put yourself to the left of that. So my interpretation for that is basically the same as the last one. It just seems like as long as you're to the left of the largest group of consecutive matter particles, that's the spot to pick. Let's look at the third circle, a bit larger this time. So for this one, I have 5 matter particles right next to each other to start off with. So my 0 index is this one right here. Not that it matters because we're in a circle, but let's look at that. And you can see this is a bit of a longer printout here, but we're still told 0. And this is, again, more that intuition that we have 5 matter particles right next to each other. It kind of makes sense that it's just at the tail end of that. So for me right now, the strategy seems to be just be to the left of the largest group. And you would think that's enough, right? I was not as satisfied just because the examples they gave us were pretty simplistic, and I really wasn't able to validate and verify that that is true for basically all cases. So what I wanted to do was to create a kind of randomizer that creates this like random circle of particles that have equal number of matter and antimatter particles, and just like try and like throw my hypothesis at it and see if it works. And actually it doesn't, and I'll show you why here. So first I'm going to show you how I make my like particles. Here I'm loading NumPy. I'm creating a function here called create particles that takes both an n, which is the number of particles for both antimatter and matter particles. So in this case 10 for a total of 20 particles. And I also wanted a seed so that I can like reduce the randomness, so you can kind of like reproduce this. If you want to code along with me, you can certainly do that. All this is doing is setting a seed so that we have consistency in our quote unquote randomness. I'm not going to go too much into the code. Definitely check it out if you're interested. This is just making the appropriate collection. That's all. So here's an example. I have create particles n equals 5, and you can kind of see what that looks like. So that's what it is. So that's nice. I didn't need a way of verifying that this is actually working, this function I made. And so you can actually import the counter class from collections, and it basically counts up each occurrence of each unique element within a list. And so it kind of looks like that basically. So I know that there are 5 negatives and 5 positives. Now I know my function works, yeah. And here I have a quick print statement, which is just going to grab the index and the value to kind of like show you what it looks like. This is as a replacement for the visual that we are provided like here. It'd be nice to kind of just see what the kind of circle looks like. I don't have a picture for this randomly made circle, so it was kind of useful to have something that kind of prints it out so you can kind of see what's like next to each other and what like makes a big group, for example. So that's why that's there. Okay, so here is me testing on larger custom examples. So here I have an n of 15, and let's check out this custom test. I have a seed of 2, so you'd have to note that. And here we have a bunch of pluses and negatives. And intuitively, I would look at this, and using my assumption from before, I would say, well, these 4 are right next to each other. That's the biggest group. So I would put it right behind this one. I put it right behind index 3. But let's check this out, and let's use our solution from before, where we make a circle from this test set, and we get the last survivor. Let's see which one wins out. It looks like the winner is actually the 0th index. So that means it's this particle right here. But how does that even make sense? Because the last time we were using like the largest group, but it seems like it's possible, just given how the rounds of annihilation work, that we're able to lead up to 0 being the 1. And if you actually look at the history here, it does make sense. You can see like things getting knocked off properly, but after round, you start realizing like, oh, there's a point where that 0 position is actually the leftmost survivor of the whole, of like a larger group. So you can see like the group kind of like combines after a while. Like here's a group of 5, right? Like that wasn't there before. And so you have to start considering kind of these successive rounds. And so I had to change my interpretation now thanks to that. And so now I still agree that you want to be to the left of like the largest group, but you have to consider these like kind of additive effects when these matter particles start clumping together after successive rounds of annihilation. You can't just like assume the largest one off the bat is the right one. Here I had another test, a custom test here, n of 30. You can see that, and you can kind of look through it, and you see that there are basically like these 2 groups of 4 here. So you might think, oh, maybe it's tied, but hold on, what about this one in the middle? Like that one gets annihilated, and so now these would clump together, and you would say, well, maybe 21 is the last surviving particle. Well, let's check it out. Let's put it into our circle and get the last survivor position. It turns out it's 50. What the heck is going on here? This is part of a group of 3. Like it's very counterintuitive that we have 2 groups of 4 here, and neither one of those is correct. It's this one. So this was really challenging my understanding and my other interpretations, because it was making it much more difficult to really like look at a single initial circle and kind of know where to pick the right value. It was dealing with like this aggregation effect that was really hard to see initially, or at least that's what I thought. And what I ended up doing was calculating this additive effect. So I mentioned the additive effect here, but I thought maybe I could actually take a kind of like running sum, or like a consecutive sum, and just like kind of loop through the entire list and kind of figure out, okay, if we start at any position, if I like add 1 for every matter particle and take away 1 for any antimatter particle, you'll kind of start seeing a pattern of like, where do we get to a point where the peaks start getting like high or very low, and that'll kind of be like the hot spot to maybe to kind of elucidate where a good spot is to pick, because ideally you would pick it at the point where you have the best chance of surviving when there are the least number of antimatter particles. So here's the code for that. Basically what I do is I have a running list here, and I'm just kind of taking the consecutive difference essentially, and I'm going to go through each particle within my previous test, the test particles too, and I'm going to calculate a value. So it's either going to be 1 or -1. So if it's a matter particle, then we'll use 1, and if it's not, we're going to use -1 because it's antimatter. And so that's the value for that particular particle type, and then I want to combine that with whatever the previous value is. So here, because I have an empty list to begin with, if there is no length, then I'll just assume 0 to start. Otherwise, it will have a length, and we can just grab the last value. So basically, I just want to grab whatever the last value was, and I'm going to add to that. So if this is a 1, then I'm just adding that, is increasing, or if it's -1, I'm decreasing it, right? So that's what I'm doing here. I'm just combining the last value with the current new value, and that will be a consecutive kind of running sum. And we'll see what that looks like here. So let's run that, and then here I'm going to print the values because I want to actually see. So we can see that we have some like peaks here. We have like a 6, but the thing I was looking for was this 50, right? Because like, what's happening at 50? Maybe there's something noteworthy there. So if I go down here, you'll notice something, that the 50 is happening right after the lowest, the most negative point in the entire graph. So what this is telling me is when you're at the index 49, that's essentially saying that at that point, you have built up so many antimatter particles that that's kind of like the worst spot to be in. But what's nice is just to the right of that is essentially the best spot to be in, because you're the furthest away from that long run of negative particles. And so that I think is what is signaling to me that this is maybe one way of actually figuring out the solution. You take this like consecutive running sum, and whatever is to the right of the lowest number is the spot to pick. So given that, my interpretation here is that by taking this like running consecutive sum, we can actually figure out the right spot. The lowest spot, whatever the index that is associated with, is essentially like the place where you have the longest run of antimatter up to that point. So you kind of want to avoid that. The way you avoid that is by going just to the right of it, because that's where you are kind of like right behind the worst of it. Okay, so that is my strategy. Unfortunately, it did require using my brain a little bit, but I think we got to something that would work. Hopefully it makes sense. And I did actually try this out on the other test examples, the ones from the video, and it actually did work out as well. So I think there is some validity to what we're doing here. So let's go check out the answer and see if we're right.
A general strategy can't rely on knowing what the circle looks like, but we can rely on how it should end, with you as the last particle standing. Let's start there and work backwards.
Okay.
Just before this, there were also some matter-antimatter pairs. Here's 3 for the sake of example. This right away suggests a strategy. You can simulate annihilations in any circle by marking all pairs of adjacent particles, then the newly adjacent pairs, and so on, to reach this final set. If you map them back to the original circle, standing to the immediate left of those final matter particles or the immediate right of final antiparticles means you'll reach this endgame state. And
oh, I didn't think of it like that. Yes, I was so focused on the matter particles, I didn't think about the antimatter particles. You can sit to the longest run of, you can sit to the left of the longest run of matter particles, but you could also sit to the right on the longest run of negative particles, because that's essentially what my solution was, which is like to like avoid the negative particles. Okay.
Survive. So here are the safe spots in all 3 given circles.
Whoa. Dude, this is too much. There are multiple safe spots? I didn't think about that. But hold on, I think I was wrong, because I found 0, which was here. Wait a second, did I code something wrong? Oh, hold up. I had my interpretation as left, which was flipped to right. I think I flipped my directions. My orientation was wrong. Because here, yeah, like this one here was my 0, but it looks like that's to the right. Oh, you know what? I think I messed up. My right and left, I got flipped. Okay. You know what? I think I might go back and rework my code because I think the logic is sound. I just think my direction is off. All right, folks, I am back, and it turns out that the list I made is going essentially right to left. This is also why conventions are bad, people. Okay, when you're writing code, do not make conventions. Conventions are unwritten, essentially. They're like the agreements that are not clear, and this is what happens. You mess up your code. What I thought was not necessary before, I'm actually using. The left is essentially what I wanted to start using. So I'm going to keep the left and right in my code here. So I am going to be using that. So for my particle, nothing's really changed. For the circle class, what I've done here is I've basically flipped the orientation. So basically the particle is now being added to the left, and we're attaching the previous particle to the right of the current particle. And for the linking of the last root is also kind of flipped. So, you know, that's the only change I really made here. I've rerun all the code here, and it does change the index here to 5 for the first circle. And I've run it all the way through, and like here is 7, and here is the 11. And so if you actually go to the video, all of those spots do line up with a valid spot in the video. There is one thing, the one caveat I will mention. I thought I was making it possible to return multiple valid spots. However, what I ended up doing was not realizing the spots that were valid after they've been eliminated. Okay, so my code does not anticipate this, and it's because of like basically large groupings that kind of like destroy themselves. So for example, with the first one, you see this, like the visual here is nice. This the outer ring here is like a complete destruction, and that's why there's only one spot. The same thing with the last one. There's only like one big ring of like complete destruction. But the middle one here, the largest ring or the largest group, has an outer destruction, basically the third round, where it is this largest one here. So that's the one that you basically have to like maintain. But these other smaller groupings are eliminated in like round 2. And so basically there's some spots in there that are just safe just because it's like basically at the tail end here. So my solution does still work for this, but there are some caveats I didn't anticipate, and my code does not account for that.
In circles, you find a good position and experience the bittersweet radiance of your new friends pairing off and becoming pure energy. You're soon left alone. But wait a minute. Today's the big day. You're an intelligent creature of
matter. No, not another one.
Out of alien races. Every 100 million years, sentient species of the galaxy send emissaries to the core to pay tribute to the galactic seed you're all descended from. Each of the 27,182 attendees has brought a cube of matter and a cube of antimatter. Except you. You've been chosen to represent your famed ancestor and reenact its moment of choice. Everyone places their matter and antimatter cubes in a ring. Your job? Pick a spot to stand where you won't be annihilated. The ring is too large to simulate annihilations like before.
Okay.
You have a programmable device you can point at spots between cubes. The device can detect the full sequence of cubes around the circle, count cubes of each type, perform arithmetic, and carry out simple logical commands.
Oh.
How do you program your device to identify safe spots?
Oh, wait, I did. Hold on. I think I did this already. Okay, it says we're looking for the general method. Don't worry about the exact language. Okay, I think I already did this. Okay, I thought I freaked out for a moment. I thought I had to do like more code. Like I thought I was done with this, but I think I actually already solved this when I was referring to the like way of using like a consecutive sum. Like I think that's something that I could that's what this solution is, I think. So I think this works. I'm going to go ahead with this because I think I already had this solution already in mind. So let's just keep going. That's interesting. Oh, wow.
Let's go back to our earlier approach, running time backwards, starting from you alone, then a sequence of pairs of cubes. A second step back produces more pairs nestled between existing cubes,
Okay.
as does the next and the next, each adding nestled pairs like a Russian doll of fundamental particles.
Sure.
A pair never forms around an existing cube because only adjacent cubes annihilate. Your survival depends on the matter particles to your right, buffering you from antimatter. We can mathematically model this idea with a sum, starting with your +1.
Oh my
For
goodness.
instance,
Oh.
this would be +1 +1 -1 +1 -1.
Yo.
From your perspective, no matter how far you look, this sum will be positive. Considering how we introduced pairs, this makes sense. Each inserted plus was immediately followed by a minus.
The sum is okay.
If we examine the starting position of any other matter cube, its sum will
Was
eventually hit 0.
0.
The
Okay.
moment that happens marks its exact annihilation partner. Again, our introduction of pairs reflects this. Nestled pairs only delay the inevitable for the outer cubes. We can now program.
Wait, well,
the
hold on,
device.
let's go back there. Nestled pairs only delay the inevitable for the outer cubes. So this is what I was talking about before. Like this whole like green large box, that's like the third round, and so anything that's like outside of that third round will be eliminated by that point. So it's always safe to be there because you're at the tail end. Yeah, math.
We can now program the device. Start a running sum with +1,
Okay.
representing you.
Let's
and
go.
Scan around the circle.
Hell yeah.
For each matter cube, add 1, and for each antimatter cube, subtract 1. If all 54,364 cubes have been scanned without the sum ever hitting 0, that spot is safe. Nothing left to do but enjoy the fireworks.
Without the sum ever hitting 0. Okay, so I think honestly, like the explanation was a bit more confusing to me, just because it involves you actually thinking about it and like the math involved. But I kind of get the math a little bit. Anyway, I consider this to be a somewhat solved problem because the part where I had to use my brain was essentially like the second riddle, which again, 2 riddles. Come on, Ted Ed, why do you keep making like riddles that are 2 riddles? That's just not a thing. So that was fun. I definitely enjoyed tackling this with an object-oriented approach and maybe using a little bit of my brain, unfortunate as that might have been. But I think I got to a solution. I'm not sure if it's exactly what he was talking about, but I think it's close enough that I mentioned like the most negative point, but he's mentioning like it should be 0, which I'm not quite understanding, to be honest. Anyway, folks, if this is the kind of content you enjoy, please make sure to like, subscribe, and do all the good things, and I will see you next time.